Good morning, class. So we're going to continue today with the combinatorial circuits. Yesterday we've looked at one that involved an AND gate and an OR gate. Today we're going to look at throwing in a NOT gate. So we haven't looked much at a NOT gate, particularly the waveforms. So we're going to go through the NOT gate a little bit first, and then we're going to do some a circuit with it and look at some waveforms for that. Okay, so today I'm introducing you more to the NOT gate. We'll go a little bit more in depth with it tomorrow. So then you'll have an assignment with that tomorrow. Okay? Alright, the NOT gate. So let's look at these real quick. So hopefully you remember a NOT gate is basically just a triangle. Here, this might be new to you. This is basically just a little circle. You can draw the NOT gate with or without it. It means the same thing. You'll see what the circle basically comes in later on when we're getting to some more complicated type gates. And the NOT gate just basically reduces to just that circle. Okay, it just makes it a little bit more easier to write. You'll see later. We probably saw this expression. I think this is when I gave it to you when I introduced the NOT gate to you. So that is the expression for it. As we start doing combinatorials, so basically it looks like the math symbols, like the plus sign for the OR gate and the multiplication for the AND gate. So we're going to start using this. So basically it's just a line over it. So that means not X. Okay. So remember, a NOT gate can only have one input. Okay, you can only take in one input, and you get one output, of course. Okay, so let's look at, I have two diagrams we're going to look at using the NOT gate. So we have X and Y inputs. X first goes through a NOT gate, and then both X and Y goes through an AND gate. Okay, so let's look at what the outputs for this would be. Okay, so I'm just going to kind of redraw this. Okay, so anytime we go through a gate, we have an output. So the output here, so if the input here is X, the output will be not X. Okay? Now going into the AND gate, my inputs then are not X and Y. So the output here is not X and Y. Okay, so what does that mean? So like once again, if there is maybe like an alarm, alarm's kind of the easiest thing to think of, you know, or like if it's in your car and you have the check engine light comes on. That's basically what dictates your car engine light. So there's a sensor. If that sensor trips on, then the signal light in your car will come on, check engine light. Any kind of security system, any kind of monitoring system runs off these logic gates. Okay, so this could really represent anything. So, but what does this output actually mean? So the alarm or the signal will sound or come on if this combination is made. So not X and Y. So remember, X or all inputs have either an on or off state. So what I mean by not X, that means when X is off. Okay. So remember, if it comes in and they're both on, they'll pass through the AND gate. So the way we do that, when we want the combinations, if you remember those truth tables, we had all those different combinations of ones and zeros. And the only time an AND gate came on is when both X and Y was 1. Okay, so I'm just going to make a quick truth table because we only have two inputs. Here's our out. When X and Y is on, then the output is on. When X is on, Y is off, output's off. When that's off and that's off, that's off. When X is off and Y is on, that's still off. Okay, that's for a typical AND gate. So the only time the alarm will sound for an AND gate is when X and Y is on. So now if we throw in this NOT gate, okay, so now we have not X and Y as our inputs. Okay, so when X is, so I'm just going to recopy 1 1 0 0 1 0 0 1. Okay, so now it's when X is not on. So here it's off. X is off, or X is on. We don't want that. X is off, but Y has to be on. And now here, X is off and then Y is on. So see how this basically changed, it inverted it. And remember I told you sometimes a NOT gate is called an inverter, and that's the reason why. Okay, so NOT just means when it's not on. That's the easiest way to think about it. Okay, so that is the Boolean expression for this little combination circuit, and this is the truth table for this. Okay, now let's look at a same thing with an OR gate. Okay, I'm just going to redraw it over here so I got a little bit more room. Now Y is going through the NOT gate, and they both are going to go into an OR gate. Okay, so now we have not Y, X, so the output here is not Y or X. Okay, so for an OR gate, I'll just do the truth table for an OR gate real quick. So output is when X or Y is on. Okay, here X or Y is on, they're both on, but at least one of them's on, so the output was on. One of them's on, both of them's off, and at least one is on. Okay, so now we're running through a NOT gate, or with NOT. Okay, so we have X, not Y, and our out. Okay, so we have 1, 1, 0, 0, 1, 0, 0, 1. And yes, I know I'm doing the truth table sideways, that's only because I kind of ran out of room. Okay, so when X is on, or when Y is off. Okay, as long as we have at least one of those. X is on, so we already know the output's on 1, because one of those is satisfied. That's what OR means, at least one condition is satisfied. X is on or Y is off. Okay, we have both of them. X is on, that's not true, or Y is off. X is on, nope, and Y is off, nope. So we get 0. Okay, so in this case, it didn't kind of invert it because in OR gate you have either option, either X is on or Y is off. Okay, but it did change this final outcome. Okay, so that's how a NOT gate will affect our circuit. So let's look at, so we looked at truth tables involving NOT gates, we looked at the Boolean expression involving NOT gates, and let's quickly go through waveform for a NOT gate. Okay, so this first one here, this is the waveform for this circuit. Okay, so we don't really need the truth table because I've changed it now. So now these are our inputs. So for the AND, we either need when X is off and when Y is on. Okay, when X is off and Y is on, the output will be on. Okay, so here we have X is on. Okay, so if we want X off, then as long as X is on, we know the output there is 0. Alright, so right here, X is off. Okay, so that's one condition. Now, as long as Y is on and X is off, the output will be on. Alright, Y is on right here and X is off right here, so that's good. So that satisfies this conditions. And then Y turns off again. Okay, X is still off, but then Y turns off. Well, we want X off and Y on, so that's not going to help. And then Y kicks back on here, but then X kicks back on. We don't want that, so that's our output. Okay, now let's look at the waveform for the OR gate. So the OR gate, remember, so the OR gate we had for when X is not on, or when Y is not on, or X is on. So X or not Y. Okay. So once again, Y is not on, so that's good. So while Y is not on, is there any time when X is on? Right here. So we know the output will be on here. Y kicks back on here. So we know the output is going to go back to off the whole time. As long as Y is on, the output is off. Then Y goes off, but X is still off. Okay, we have to have Y off and X on, so that is off. So there's our output for that. Okay, hopefully you're able to work through these kind of on your own and follow it along pretty well. If you have questions, just get with me on Teams. And don't forget, take a picture of your notes, submit it for today, and that's it. All right, have a great day.